Hi, my name is Matthew Kong, and welcome to my project on the machine learning algorithm for the classification of drowsy versus alert drivers. Did you know that drowsy driving causes an estimated 100,000 crashes per year? In fact, the National Highway Traffic and Safety Administration estimates that drowsy driving results in 1,550 fatalities, 71,000 injuries, and 12.5 billion in monetary losses each year. Clearly, drowsy driving is a serious problem that needs to be addressed. That's why we developed a machine learning algorithm that uses facial recognition technology to detect when the driver is going drowsy. Our image classification algorithm in Python uses the eye aspect ratio to determine when the driver is drowsy or has fallen asleep. If the program detects eye aspect ratio below a certain threshold for a certain number of frames, a sound will be played to awaken the driver. The code uses a convolutional neural network, otherwise known as CNN, to detect whether eyes are open or closed. It uses the TensorFlow library with the Keras API for building and training the model. The model is trained on a dataset of images of open and closed eyes. When searching for this dataset, we made sure to find one with enough pictures and different individuals. It was very important for us to find a diverse dataset to ensure that the model works well with anyone who wants to use it, regardless of their physical appearance. The output is probability, indicating the likelihood of the eyes being closed. The model is then compiled and trained using the Atom optimizer and binary cross-entropy loss function. To make use of this trained model, we import TensorFlow, OpenCV, and NumPy libraries into the detection software. We define a function to calculate the eye aspect ratio, or AIR. We load the trained model in HAR cascades for face and eye detection. We then open the webcam and start to loop and capture frames. We resize each frame into a shape that the model takes, which is a 64 by 64 RGB picture. Then we can detect faces, and for each face detected, we can then go on to detect eyes and calculate the AIR. If AIR falls below a threshold for a specified number of consecutive frames, we trigger an alarm. However, the algorithm is not without its limitations. It struggles more in low light conditions, and the detection of drowsiness in drivers who wear glasses is also something the algorithms struggle with. There's also a risk of overfitting the model and false detection of nose, mouth, as well as the eyes. Here we can see on the top right is an example of low light conditions, slightly lower light conditions. And on the bottom left and right, we can see errors in detecting the nose and mouth as an eyes. And here is an example of what the camera sees when someone is starting to fall asleep, when their eyes are squinted. So despite some of these limitations, we're already working on creating a standalone product that will alert drowsy drivers. A prototype is already in the works based on the Raspberry Pi system, which has the necessary computing strength to process these images. We plan to train the model on a larger data set and include individuals with glasses in this. Infrared technology is also a possible way to combat the low light situations without the driver needing distracting interior lights on. We also plan to create a program that can progressively incorporate images of the customer into the dataset and then retrain the model accordingly to tailor to each individual user. Research implementation with the car audio and light systems for more effective routing is also in progress. With our algorithm, we hope to reduce the number of accidents and fatalities caused by drowsy driving and make roads safer for everyone. Thank you for listening to my presentation.